This is a tutorial to perform an FSI problem using LS-DYNA. So let's say we want to do water impact simulation. A minimum control cards needed to perform a multi-material fluid structure interaction problem using LS-DYNA is as follows. Star control ALE, star ALE multi-material group part, star section solid with element formulation 11, and star mat. For water and air we can use star mat null. Also we need an equation of state for water and air. Equation of state used for water is Grunsian, and equation of state used for air normally is polynomial. The fluid structure interaction, that's the interaction between the Lagrangian and the Eulerian part, is done with star constrained Lagrangian solid. So let's say now we want to perform an Apollo drop into water. So we're going to have three parts. So we generate our mesh. This is the part, the red part here, which is air. We generate the green part here, which is the water, all solid elements. And there's merge nodes between the interface between air and water. These elements have to have a common node. And then anywhere within the air, we're going to put the Lagrangian part, and the mesh between, there's no connectivity between the Lagrangian and the Eulerian parts. The only interaction is going to be with star constrained Lagrange in solid. So if we look here, we're going to see part 1 is the air, part 3 is the water, and you have this Apollo. So for example, we put this Lagrangian part, which is the Apollo, barely touching the water part. So this is the entire mesh. In terms of the boundary conditions, so for example, if we want to do this in a pool, we take all the outside nodes and we constrain the degrees of freedom. So no water will go out of this pool. So let's see the input file. There is the input file for the problem. So star control ALE, anywhere within the input file, you can take all the default values if you do not want to change anything. We also need star ALE multi-material group part. So part 1, which is the air, and part 3, which is the water. These are two different multi-material groups in which an element can be filled either with group 1 or group 2 at any given time. Then we need the part for the air. So we need the star mat null for the air, and we can see there are the properties for the air. And this material needs an equation of state, so star EOS linear polynomial, and star section solid element formulation 11, which is multi-material formulation. Then part 3 for the water, again section 3, material 3, and equation of state 3. There is the star mat null with water properties. This needs an equation of state, which is Grunsian. So there is the Grunsian equation of state for water properties, and then star section solid with element formulation 11. Normally the hourglass control for water, we need to set the hourglass coefficient to a very small number, 1e to the power minus 5 or minus 6. So we have everything except the interaction now between the Lagrangian part and the Eulerian part. This is basically with star constrained Lagrangian solid. So the slave would be the Lagrangian part. These are the solid parts. And the master part is going to be the fluid. So this one here means that 10 is a part ID, and that part is the Apollo part. This 0 means that 11 is the part set ID, and there is the part star set part 11, which has part 1 and 3, which is the water and the air. 0 means that is a part set. 1 means that's a part ID. Number of quadrature point, that's the number of interaction point between the Lagrangian and the Eulerian. 3 means 3 by 3 within the segment of the Lagrangian is going to interact with the fluid. C-type, that's a coupling type, which is type 4 penalty formulation. And then you have the direction 2, which is compression, tension between water and air. As a matter of fact, this is the only card required for the interaction, and I basically can take all the default values, except I need to define the master and the slave if I wish to take all the default values. So only minimum requirement for star constrained Lagrangian solid is to define the slave and the master. The slave normally is the Lagrangian, and then the master is normally the Eulerian. So now that we have this file, we can run it. I did. And now to simulate, obviously, if I now animate here, I'm not going to see anything because this is an Eulerian part. The mesh is stationary. So to visualize the problem, I need to go to parts, and then in here the ID for the part. So I look for fluid ALE in the assembly and select part. So click on this, then 2 additional ALE group will show up in the part list. So I have group 2, which is the water, group 1, which is the air. So let's click on group 2, which is the water, and also put the Apollo part 10 as well. So now I'm gonna see the following. Go to shade, so I'll see the Lagrangian part, and then I can start animating. So now we see the Lagrangian part hitting the Eulerian part, and here in this case the Apollo impacting the water. We need to make sure that there is no leakage of the water inside the Lagrangian. This concludes the tutorial.